Alright, so today we're going to look at Chapter 2, Big Concept Number 6, Parent Graphs and Transformations. I'm learning to identify, graph, and describe parent functions, and I am learning to identify and graph transformation of parent functions. Now, there are tons of parent functions out there, but we're primarily going to focus on only two types today. But first, a parent function is the simplest function of a family. It is the simplest. So, what does that mean? Well, from our previous notes, you know what the absolute value function is, but let's dive into it a little bit further. The absolute value is f of x is the absolute value of x, where x is surrounded on both sides by these vertical bars. Now, if we were to make a table of values with x and y, and used our trusted -2, -1, 0, 1, and 2 values, we would see that -2 becomes +2, -1 becomes +1, 0, 0, 1, 1, 2, 2. It makes that very distinct V shape. So we're going to go ahead and plot that V shape. So there is our very distinct V shape. Our domain, when looking at all of our x values, is -infinity to +infinity. And our range actually starts at the value of 0. And we can include 0 because it is a solid dot. So we go bracket, 0, comma, infinity. Now we have one intercept. It is both an x and y intercept. And it is at 0, 0. This is the parent function. All absolute value functions are based off of this specific graph. Next, let's take a look at the quadratic function. A quadratic function says f of x equals x squared. So when we go ahead and make a table of values, we have x, we have y. We'll use our 5 trusted values, -2, -1, 0, 1, and 2. -2 squared is -2 times -2, which gets us that +4. -1 times -1 gets us +1, 0, 1, and 4. So it's similar to the V shape, but it's actually different. So when we plot -2, +4, -1, +1, 0, 0, 1, 1, and 2, 4, we actually end up getting a U shape. So we have a U shape. So looking at our domain, notice, if this graph were to continue on in the positive x direction, would it stop? It wouldn't. And the same with this -x. It wouldn't either. So our domain is -infinity to infinity as well. Our range, our smallest y, starts at 0. It includes that value and then continues on and on forever for a positive infinity. Our intercepts, we only have one, and it's both an x and y intercept of 0, 0. This is the function all quadratic functions are based off of. They all have transformations from this point on. So, what is a transformation? A transformation is a change that occurs to a parent graph such as a shift, reflection, compression, or stretch. So here is a very, very basic example. We have A, H, and K. So A is that leading coefficient, that number out in front. So if it is negative, that means your graph is reflected across the x-axis. All right, so if it's negative, it reflects across the x-axis. Now, A has a special place too. So if A is a value greater than 1, it is going to stretch out our function. And if it's a value between 0 and 1, it's going to compress it. All right, let's take a look at our H. Our H if positive, shifts to the left, and if negative, shifts to the right. All right, and then lastly, we have K. K is almost opposite of H in the fact that if it is positive, it shifts the graph up, and if it's negative, it shifts the graph down. All right, so altogether, those make up what we call our transformations. With those identifiers, we can actually graph most any function if we know and understand the parent function well enough. So let's take a look at some examples. Write and graph the transformations. Well, first, what is my parent function? My parent function for this one is the absolute value of x. So I'm actually going to draw the absolute value of x so we can see where those transformations are coming. So I know that the absolute value of x is negative 2, 2, negative 1, 1, 0, 0, 1, 1, 2, 2. It is that distinct V shape, so I'm going to draw the V shape. All right, so my parent is here in the pink. Now, I need to figure out what my transformations are. So inside my absolute value, I have a minus 3. So that means I'm going to shift my graph to the right 3 units. And the 4 says I'm going to shift my graph up 4 units. So every point on my current absolute value function will go to the right 3 and up 4. So starting from 0, 0, 1, 2, 3, 1, 2, 3, 4. And then when I move the rest of them, they follow suit. And just to show you, 1, 2, 3, 1, 2, 3, 4. And then I draw my distinct V shape once again. So here we have our parent function. We'll call f of x. And our child we'll call g of x right here. All right, let's go to the next one. We have f of x equals 2x squared minus 5. My parent is x squared. So I know that x squared is negative 2, 4, negative 1, 1, 0, 0, 1, 1, and 2, 4. It's a U-shaped, so I'm going to draw my U. So I have my U-shaped. So now let's look at our transformations. We have a whole number of 2. That whole number says I'm going to stretch my graph by a factor of 2. Let's write a little bit nicer. Factor of 2. The minus 5 says I'm going to shift down 5. So first things first, I'll go ahead and do that shift down. 1, 2, 3, 4, 5. Here's my new vertex. And now, when it's a whole number of a factor of 2, we're going to double the space between our points. So this first point, it has a space of 1 going up, so now we're going to have a space of 2 going up. This one had a space of 3. Now we're going to have a space of 6. 1, 2, 3, 4, 5, 6 over 1. Perfect. And then I'll do the same thing over here. Double my original space. Instead of going up 1, I'll go up 2. Instead of going up 3, I'll go up 6. And then I'll make that U shape again. All right, so now we have that U shape again. Let's take a look at that domain and range of our child function. Our domain still goes off in either direction, so that hasn't changed. It's still negative infinity to positive infinity. However, our range now drops down to -5 and continues up to positive infinity. Over here, because I forgot to do it earlier, our domain hasn't changed. It's still negative infinity to positive infinity, but our range has changed. Our lowest y value is now at 4 and goes to positive infinity. All right, going to the next two examples. We have a square function again, that quadratic, so let's go ahead and draw that parent function of f of x equals x squared. And I've been doing it in pink, so we'll continue it with in pink. All right, so now let's take a look. Here, we are going to reflect across the x-axis. This 1/3 says we are going to compress, push down, almost flattening it by a factor of 1/3. And then the -4 says right 4. So first we're going to go to our right 4, and this time we know that we are reflected. And because we're reflected, we're going to go in that negative, the y values. So when we say compress by 3, our next point is going to be over 3 and down 3 on either side. Now, for example, if it was compressed by 1/4, we'd go over 4, down 4, compressed by 1/5, over 5, down 5. So now we've compressed it, and we're only going to do those 3 points because they're super easy compared to the rest. And eventually, when we get to our parent functions, I only will ask you to plot the first 3 values, which makes it easier for you. All right, and then we're going to draw a reflection across that x-axis. And there we have it. So our domain, still the same. We're still going off in either direction of our x-axis. So we have negative infinity to positive infinity. But our range now has a smallest of negative infinity and goes to 0. And because it can touch that 0, we have a bracket. All right, next example. We have y equals the negative absolute value of x minus 2. The parent function for this one is the absolute value of x, which is that distinct V shape. So we're going to go ahead and draw the parent function so we can visualize the transformations that are going to occur. All right, so we have that distinct V shape. The minus says that we are going to reflect across the x-axis. And the -2 on the inside says we're going to go right 2. We're going to shift that right 2. So we shifted it right 2 and we reflect it. The points go in the opposite direction. Once again, we'll have that very distinct V shape. So go ahead and draw it. So let's take a look at our domain. Our x values, once again, are not changing. We're still going off in either direction from left to right. So we have negative infinity to infinity. However, our range is affected. Our smallest value is now negative infinity, and our largest is 0. So we put 0 in brackets. All right, so now we're going to work backwards. We're going to start with the transformation, and you're going to have to tell what they equation is. So here our parent function, if this is a parabola, what is our parent function going to be? If you said a quadratic, x squared, you would be absolutely right. So f of x equals x squared. So our transformation would be f of x equals, all right, now let's take a look. Here is our current vertex. We know our original vertex always starts at 0, 0. So we went right to, down to, and it looks like we have a stretch of up to over 1, so a stretch of 2. So when we put this all together, we get a for our 2, x minus 2 squared minus 2. So right is the minus 2 here, down 2 is the minus 2 at the end, and the stretch of 2 is that 2 in the beginning. All right, last example. We know that we always start at 0, 0. It is still a parabola, so our parent function is f of x squared, and we went all the way to -1, -4. So that means for our transformation, we went left 1, down 4, and once again we have a stretch of 2. All right, so that means that transformation gets us f of x equals 2 quantity x plus 1, because we went to left, squared, minus 4, because we went down 4. All right, so that is our little bit about transformations. We'll touch upon that again throughout the year as we spiral through the curriculum. If you have any questions, let me know. I'm always here to help.